Hello students, I believe that you all are getting benefits of our videos, and you can ask me on my personal number regarding your doubts. I am always there to help you. Then now I am going to cover a very important topic, that is colligative properties. Colligative properties of a solution are those properties which depend on number of solute particles, not on their nature. So this is very important definition. Such properties of solution which depend on number of solute particles, not on their nature. So first I will explain these lines also, that what do we mean by these lines. Like if a solution containing 1 mole of glucose, okay, so 1 mole of glucose, when dissolved in solution, the solution will contain 6.022 into 10 to the power 23 particles of glucose. These are the solute particles. So the properties, those properties of solution which will depend on these such numbers, those will be called colligative properties. Here glucose will of course be in molecular form. Now if we take a solution containing 1 mole of Na plus ion and 1 mole of Cl minus ion, so here the total number of particles are 2 moles, and you all know these 2 moles are obtained by dissolving only 1 mole of NaCl. See, I am explaining very important concept. Pay attention that we are dissolving 1 mole of glucose, we are dissolving 1 mole of NaCl, but the properties of both the solutes are different. This is non-ionizable solute, so it will remain in the molecular form, and the total number of particles will be equal to Avogadro number. Why? Because NaCl is the ionic solute which has the tendency to get 100% ionized, and on dissolution it will dissociate into 1 mole of Na plus ion and 1 mole of Cl minus ion. So the total number of moles, the total number of particles present in the solution would be 2 into Avogadro number. So the properties of that solution will depend on this much number of particles. So again and again I am saying, so in colligative properties we will focus on those properties which depends on number of particles, not on their nature. Here it doesn't mean these properties will not depend whether the solute particles are ions or molecules. It is the meaning of this definition, that here the total number of particles will be considered 2 moles. Here the number of particles will be considered 1 mole. On prima facie it seems that both are having the same concentration, but both solutions are having different number of particles, so their colligative properties will of course be different. So now there are 4 types of colligative properties in our class 12 syllabus. So you have to first learn the names of those properties. The first is again what we have studied, that you all would be able to recall: relative lowering in vapor pressure, then elevation in boiling point, then the third colligative property is depression in freezing point, and number 4 is osmotic pressure. So these are the 4 colligative properties we have to understand, and we have to solve their numericals. So relative lowering in vapor pressure, ये सबको याद आ गया होगा क्या है ये? राउल्स लॉ फॉर नॉन वोलेटाइल सॉल्यूट, जिसमें वेपर प्रेशर में कमी आती है. किसके वेपर प्रेशर में कमी आती है? सॉल्यूशन के, क्योंकि सॉल्यूट कुछ एरिया को कवर कर लेता है और वेपर प्रेशर कम हो जाता है। तो अगेन इसका मतलब रिलेटिव लोवरिंग इन वेपर प्रेशर हम पढ़ चुके हैं और इसका फॉर्मूला सबको याद हो गया होगा, दैट वुड बी P naught minus PS upon P naught equals to XB. So nothing new we are studying, we are recalling the previous thing, that is Raoult's law for non-volatile solute. This is means relative lowering in vapor pressure is one of the colligative properties of solution. Then the second thing is elevation in boiling point. If you can understand this concept, you can better understand this concept, because you all know these two terms are interrelated. Because according to latest definition of boiling point, boiling point is the temperature at which the vapor pressure of any liquid becomes equal to atmospheric pressure. So this is the definition of boiling point. So elevation in boiling point and vapor pressure are interrelated and they are inversely proportional to each other. You have to keep in mind that vapor pressure and boiling point is inversely proportional to higher the vapor pressure, lower the boiling point. So they two are inversely proportional to each other. And when now we have to understand that what about solvent and solution. Now solvent and this is for solution. So these two, how these two colligative properties are interrelated with each other, I am explaining you. Solvent has higher vapor pressure than a solution. We all know this thing. Pure solvent has higher vapor pressure than solution. So definitely the temperature at which there is sufficient vapors which are exerting pressure on the surface of liquid, that is equal to atmospheric pressure. That particular temperature, that much temperature of the solution will be called its boiling point. So we all know that if higher the vapor pressure, soon it will become equal to atmospheric pressure and the liquid will attain its boiling point. So when the vapor pressure is higher, definitely the boiling point TB naught, see this is denoted by TB naught. Naught is always for pure condition. So solvent in its pure form TB naught, this is boiling temperature for solvent. So of course TB naught will always be less than TB. TB is boiling temperature for solution. So see these four terms, because P naught is greater than PS, so TB naught will be lesser than TB. Because when we will put, suppose if we will put salt in it, so there would be lesser vapors. So that vapor will exert lesser pressure, and that pressure will not become equivalent to atmospheric pressure. So you need to heat the solution for longer time. The temperature will raise, and then at increased temperature, with rising temperature, there would be sufficient vapors that would equalize the atmospheric pressure, and that particular temperature will become the boiling point of solution. So these two terms are very, very important. P naught greater than PS, so TB naught would be lesser than TB. Okay, so this is elevation in boiling point, because vapor pressure is lowering, that's why boiling point is increasing. So it means boiling point of solution is always more than solvent. So what is the daily life application of this observation? Now see, if you have to boil or cook the pulses like rajma, chola, which take more time, so what you can do, you can increase the boiling point of water. How? You can add salt in it, because when you add salt in water, the boiling point of the solution increases, and now your water, that solution will heat at 105 or 1010. You all know that in pressure cooker the water boils at 112 degrees Celsius. So you can rise the temperature of the boiling water, and so your pulses will be soon overdone. So दिस इज द डेली लाइफ एप्लीकेशन कि अगर आपको दालों को जल्दी गलाना है, खाना जल्दी बनाना है, सब्जी को जल्दी गलाना है, तो नमक पहले डाल दीजिए, क्योंकि नमक डालते ही बॉइलिंग पॉइंट बढ़ जाएगा. ठीक है. सो एलिवेशन, नाउ वी विल सी द graphical representation, that if we plot a graph between temperature and vapor pressure, then there would be two graphs we have to understand. Suppose here we are taking the vapor pressure that is equivalent to 1 atm pressure. So now see how we will see that for any solvent, suppose water, if we are starting with at a particular temperature, suppose we are starting with room temperature, if the temperature is in Kelvin, so room temperature means suppose at 298 Kelvin we are starting, and if we are increasing the temperature, so the boiling point will, so the vapor pressure will increase, because more pressure, more vapors will be generated and more pressure will be exerted. So as we increase temperature, the vapor pressure increases. Vapor pressure increases, and when the vapor pressure becomes equal to atmospheric pressure, that particular temperature is called, that corresponding temperature is called what? This is called boiling temperature. And if this is the graph for solvent, so that would be TB naught. Now, if we dissolve salt in that particular solvent, so that will no more solvent, that will become solution, and of course at that same temperature its vapor pressure will be lower. So definitely the curve of solution will always be lower to that of solvent. So this is the curve for solution. You need not to mug up that solution curve is lying below the solvent curve. You know that P naught is greater than PS. So this is the depiction. Vapor pressure of solution is always lower than solvent, and when you are increasing temperature, the vapor pressure is increasing. And now see, at this temperature, suppose this is water, so if the pure water has boiling point 100 degrees Celsius, so when you are adding salt in it at 100 degrees Celsius, it is not having sufficient vapor pressure, and this vapor pressure is not equalizing this atmospheric pressure. So what you have to do, you have to heat up further the solution, and by increasing temperature, at rising temperature you will find this particular temperature where this vapor pressure is becoming equal to atmospheric pressure. So you see, this is the increment in temperature, the boiling point. That's why we call it elevation in boiling point. So this would be TB. So if I say that what is the change, so that is change in boiling point, that is elevation in boiling point. How much elevation? That is TB minus TB naught. TB minus TB naught is the change in boiling point. Suppose for simple example, if I say that boiling point of water is 100 degrees Celsius, so on dissolving 1 teaspoon of salt in it, the boiling point will raise up to 100.51 or 100.31. There would be some increment in the boiling point. Now we are studying that elevation in boiling point is the colligative property. It means this rise in temperature, this elevation in boiling point would be depending on the number of solute particles. So it is observed that TB is directly proportional to molality. We are saying here the term molality. We could have said that TB is proportional to capital M molarity, but we are not taking molarity. Why? Because you know molarity is temperature dependent, because we are dealing with higher temperature, and temperature changes the volume, so molarity of solution can change. That's why we are using molality here, because molality is temperature independent. So number of moles of solute particles in terms of molality we take it, and that sign would be replaced by some proportionality constant Kb into M, and this Kb is called, very important, this is called bulioscopic constant. So 1 mark question comes, define bulioscopic constant. So how will you define bulioscopic constant? So if we consider, if M is 1, if 1 molar solution is there, so how will you define a bulioscopic constant? Bulioscopic constant is the rise in temperature for 1 molar solution. Once again, bulioscopic constant is the rise in temperature for 1 molar solution. If we take 1 molar solution, so whatever the temperature rises for boiling point, that would be its bulioscopic constant. So this is all about this topic. If you have any doubt, you can contact me personally. I will be always helping you. Thank you.